5 minus. This happens to tell you it's shaped like a V. Okay? All right. So when I'm drawing this, well, let's first do the valence electrons. If you're not in my class, this is my style. Count the number of valence electrons first. 5 iodines in column 7 of the periodic table, plus 1 for that minus charge, 36. Now I'm going to go over to scratch paper over here. I will not draw this. So my next step is to draw the skeleton of this. Just what is it generally, what's the general connectivity? I'm not drawing that. The reason I won't draw that is it's impossible in the English alphabet for that to ever look like a V. Okay, so that could not be shaped like a V, and the question tells me that the whole entity is shaped like a V. Okay, so I may have guessed that, but without information here, but given that information, I'm not going to guess this. Usually you do that kind of shape. So I'm going to put this just in a line, because if it bends the right way, it'll look V-shaped. There. So there's my skeleton, just connectivity right in a row. This is not doing shape yet. We're going to get to shape as soon as we fill in, do all our Lewis and stuff like that. So out of 36 electrons, I've used 2, 4, 6, 8 of 36. Then my styles go to the outermost atoms. 8, 10, 12, 14. There's an octet. Then 16, 18, 20. There's an octet. Now I'm going to make my way to the inside. 22, 24, 26, 28, 30, 32. So I have 32 of 36, but everything has an octet. Where would you like to put those final 4 electrons? There's a lot of central atoms, so I'll number them. 1, 2, 3 for the middle, 4, and then 5 there on the end. Okay, so you want 4 electrons on 3. Just want to make sure I got it. Okay, so let's do that. Okay. All right, let's talk about shape, and let's see how this shape kind of turns out. So I'm going to abbreviate EG for electronic geometry and MG for molecular geometry. For this atom, what's electronic geometry? 4 groups, so you'd say tetrahedral. 2 of those groups are lone pairs, so you call it bent. Same for this one. I'll just put the arrow all the way over there. That one, number 4, has 4 groups. Oops, let's zoom out a little bit. 4 groups, 2 of them are lone pairs, so it's a tetrahedral bent. I don't know about your world, but in my world, this will never look like a V, because this will take on some sort of weird shape like this. Who knows what that middle one will be, but it's just not V-like. So based on the question, this cannot be what I'm looking for. So I have to restart again. Let's do that. So we're going to restart, redraw the skeleton the same way. Okay. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Where do you want those last 4 electrons? Yeah, 2 and 4. Let's do that. Here and there. They're also central atoms, so you can also do those. Okay. So now, again, I will do EG for electronic geometry and MG for molecular geometry. Okay, let's do the middle one first. It's the same as what we saw above, 4 groups. So it's tetrahedral and then bent. 2 lone pairs, just like the ones up above that we did. Okay. This one and this one are going to be the same. What's the electronic geometry? You should see 5 groups, so that's trigonal, bipyramidal. Okay. When the 3 of them are lone pairs, what do we call the molecular geometry? Yeah, linear. Okay, this is shaping up like what I want. I believe this is my correct structure. So let's kind of finish it off. The not showing the shape, I at least want to put the brackets in the minus charge. Okay, let's show the shape though. Got I. This one in the middle is bent, which is going to give me that V shape that I was looking for. The linear for the second and the fourth iodine, keep it along the line. So I'm good there, and that is the structure I was looking for. Let's double check the formal charges though. We just want to make sure those are okay. Let me give you a 10-second head start on me. Figure out all the formal charges. They better be 0, +1, or -1 to be happy. Not for the molecule to be happy, but for us to be happy. Okay, what do you get for this one? Let's do the one on the outside, that one right there. 0, so the one at the endpoints are 0. How about this one? -1. If you're in my class, you count 1, 2, 3, 4, 5, 6, 7, 8. That's over 1 by the column number. So you get a -1. And then here, +1. All right, looks pretty reasonable. V-shaped, everything I was kind of looking for. We know this actual bond angle. Let's put in the bond angles. So linear, this should be 180. This one should be 180. This one, the ideal, so it's actually 95. But what would be the ideal? 109.5. So if it actually bent according to the way we had predicted, it'd be 109.5, but in reality it's just 95. We know it's 95 because that's what the question said. Okay, let's do a couple other things here. Polar or non-polar? This is definitely polar. In my class, the electron distribution is asymmetric, is the way I explained it. Let's count the sigma and pi bonds. How many sigmas? I'll do the easy one. There's 0 pi bonds. Sigma? 4. Let's see what else we can calculate here. We did Vesper, sigma pi, Lewis, polarity. There's no real resonance here. Hybridization. Yeah. Let's get a different color. Okay. I'll do purple light. So blue. I don't know. What's hybridization right here? 5 groups. So sp3d. Same with this one. sp3d. And then this one in the middle? Yeah, 4 groups, so sp3. Hybridization is based on the group count. So the middle one, I count 4, so it's sp3. The second and the fourth carbon, 5 group count, so sp3d. All right. Any questions on that? I want to do a little bit more with sigma and pi, and a little bit more with hybridization. Okay? While you're thinking about that, or mumbling, or whatever you're up to up there. Yeah, there we go. Okay, for this one, oh, can you kind of not see it? There we go. I want you to count the number of carbon bonds, not carbons, number of carbon atoms, hydrogen atoms, sigma bonds, pi bonds, and then we'll do the hybridization on each central atom. You want me to give you, what, 30-second head start? Yeah, nice. And feel free to just work with a partner or keep on going once I get started on it. I have to count too because I just made this up.
triple one is 5 hydrogens.
If you don't want to see it, I'm going to move this and put my answers off screen.
Hydrogen, sigma, pi, and heavy.
Oh my gosh. Oh my gosh.
No.
Well, you all will double check my answers, so I'm good. Okay, I'm kind of guessing too. All right. For those who want to play along, how many carbons did you get? I think I got 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. How many hydrogens? 7. Oh, I thought I got more than that. 1, 2, 3, 4, 5, 6, 7, 8. 3, 9. I think that 9 is correct. How many pi bonds? If anybody got that yet? I think I got 5. 1, 2, 3, 4, 5. Double count with the triple bond. So 1, 2, 3, 4, 5. Sigmas was the really annoying one. Sigmas is the total bond count. So I'm going to put a little brown mark if I counted it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Cool. I think I got it. Somebody count slightly. If I missed something, let me know. Yes? Yeah, I like that. I'm going to redraw it. It got a little messy. The question is why the oxygen doesn't have an octet. I'll let people percolate on that. It's not because I messed up. If that's what you would want to do. Okay. Anybody know why that doesn't have an octet? Because I didn't draw the lone pairs, and you should. There's 2. What else doesn't have an octet, seemingly? Nitrogen. Yeah, I should have drawn those lone pairs too. Don't expect us to do those, so if you don't know how that works, look at the periodic table, start at carbon. Carbon, when the formal charge is 0, is going to have 0 lone pairs. It's going to count 1, 2, 3, 4 as you go over. Nitrogen will have 1, oxygen will have 2, fluorine will have 3, etc. Neon would have 4. The bond count is similar. You just count opposite. So carbon will have a 4 bond count. Then nitrogen 3, you'll see 3 there. Oxygen 2, you'll see 2 there. So fluorine 1, neon would have 0, etc. Yeah? The TA said you could do lines on instead of lone pairs. I've seen that before. I don't do it in class just because aesthetically I don't find it pleasing. But you're right, people do this. So that counts. And I'm not grading the Lewis structure question, so I won't be upset in my heart, you know, so it's fine. You like those? Yes. How do you know that 3 hydrogens are trapped in nitrogen? You mean not 3 hydrogens? This is a carbon here. This is a carbon here. How do you know 3 hydrogens are attached to a carbon? Because carbon always has 4 bonds. So if any bonds are not shown, it's a hydrogen. So in the same way there's hydrogens here, because you only see 1, 2, 3 bonds, so anything undrawn is a hydrogen. That's always true. If you're in my class, that was covered on page 15 of the reader. Okay. Hybridization. Let's do that. Okay, last question, then I'll have to go on. But yes. You want me to recount the sigma bonds? Okay. It's where the brown marks are. 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Every bond counts as sigma. Every bond counts as a sigma. Okay, good. Hybridization here. sp2, 3 groups. Here? They're all, yeah, all of these here. All of those are sp2. Okay, that one right there. Yeah, that one's sp3. It has 4 groups. Remember, the hydrogen is not drawn. It would be up for you to draw it. This one, the nitrogen. Yeah, sp3. Remember, you have to draw the lone pair if we don't draw it. And so some people would wrongly get sp2 here when it's really sp3 with the lone pair. And then this and this. Both sp, they both have 2 groups. And the last one we didn't do was this carbon down here. It's also sp3, has 4 groups, 3 undrawn hydrogens. Those are drawn up here at the top. So every carbon has 4 bonds. If a bond is not drawn, it is a hydrogen. All right, good. Good we did that one. A little fuzzy for some of you, that's okay. You still have about a week before the final, so you're chilling. Oh, okay. Okay, that was a rough reaction. Did I answer your hybridization questions? If no, raise your hand, because there are more things, but I'm going to move on and I got it all. Yes? I could, but this would be a structure we would never do that for. Do you want me to draw for something else? Like what? CH4, C2H4, C2H2, C2H2. A hybridization scheme, not scheme, but really the hybrid orbitals of C2H2. That's this. Each carbon, just like up above, each carbon is sp hybridized. What does sp hybridized mean? That means that each carbon has 2 sp hybridized orbitals. I'm going to put the word 2. Oh gosh. 2 of, maybe I'll do this, 2 sp hybridized orbitals and 2p unhybridized orbitals for each carbon. Each carbon will have that according to the hybridization scheme. So if you're going to draw this out, you would say, okay, here's carbon and there's carbon. There'll be a hydrogen over here and a hydrogen over there. Okay, so I'm going to draw what kind of looks like the Lewis structure except with the hybrid orbitals. So each carbon has 2 sp hybridized orbitals. Like this. Okay? Each carbon will both have 2p unhybridized orbitals, and they're both orthogonal to what you see right now. So they're in the Cartesian coordinate system. So you'd have one kind of vertical like this for each. Now let's label these just so we don't lose track. This was a sp. This is a 2p. 2p. sp. 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 Okay. Okay. Each carbon, remember, has 2 of the 2p's. So there's one more. This is great. This is going to answer another question that was on the thing there. I'm drawing this, trying to show it go in and out of the page or the screen. So it looks diagonal. It's trying to show it going in and out of the screen. Okay. So these are going forward and backwards. Those are all also 2p, and they're not hybridized. Both sides, like if you're looking at this one, both sides are one orbital. So remember, a 2p looks like this. It's shaded partway through. So every one of these orbitals have one electron. If you remember back to the hybridization scheme, if you're hearing the word hybridization scheme and not knowing what the heck I'm referring to, hypothetically, then let me show you what I mean when I say that word. This is like 14.1, I think, in the text. If you have my reader, the hybridization scheme for SP is on page 125. It looks like this. So that's how I knew there was 2 SP hybridized orbitals and 2 2p orbitals. Each orbital has 1 electron. So that's how I knew that. I know that. So yeah, that's where it comes from. That's where this knowledge comes from. Each one has 1 electron. Here, here, and then here and here. I'll put black dots for the electrons. There and there. And there and there. Okay. The hydrogen atoms I haven't drawn yet. Does anybody know what kind of orbital it would be?
S.
S, or 1s. You know that from the electron configuration. Hydrogen is 1s1. So just be a circle or a sphere. They would also bring 1 electron. As such. Okay. Now look where my pen is. What kind of bond would that be right here between the carbon and the hydrogen? That's a sigma. You know that because if you look between the midpoints of each orbital, the overlap of the orbitals happens along the midline. How about this bond right here? Also sigma. If you look along the midline between the center points of each orbital, the overlap happens right here in the middle. Likewise, this is also sigma between this CH bond right there. Okay, these two 2p orbitals will make what kind of bond? Pi. We draw those. They are actually touching. It's hard to draw it beautiful and touching at the same time, so you often see people do this. That's a pi bond. You'll see if you look between the center points of both orbitals, the overlap does not happen along the midline. And then these 2 orbitals will likewise pi bond. There's a pi there as well. So a triple bond has how many sigma bonds? 1. How many triple bonds? Pi bonds, sorry. 2. So you see this carbon-carbon bond is a sigma and 2 pi's. So there's the 1 sigma and 2 pi's. What you would want to be able to do on this kind of diagram would be to label it. So make sure you could figure out what the hybrid orbitals are, where the 2p orbitals are, where the sigma bonds are, and where the pi bonds are. That sort of thing. You should also be able to figure out the hybridization of each atom. We already talked about that. But for example, this atom here is sp hybridized. Another hint with sigma and pi bonds, if that's a little fuzzy, sigma bonds always occur between hybridized orbitals, in this case sp, and then the pi bonds are occurring between 2p orbitals. So if you see 2p orbitals, they're making pi bonds. If you see hybridized orbitals like sp, sp2, sp3, in our class they're always making sigma bonds. It could get more advanced in other classes. Yeah, there you go. How did I determine how many p orbitals to draw? If you back up 1 step, I'll zoom out. I I know that every carbon has two 2p orbitals. If you back up one step from that and look at the hybridization scheme, sp hybridized has two 2p. So that's something to stick in your brain. I get it from drawing this in my head. But however, that works for you. Yes? Do all the Chem 2A professors, yes, have the same test? Why is that 5 minus polar? Because it has an asymmetric distribution of electrons. So you have, on the top half, electrons from the iodine atoms, those 4 up there on the top. On the bottom is just their lone pairs. Those are not symmetrically distributed. So asymmetric distribution of electron density is what we call polar. It would have a dipole. Yeah. So I tell my class, just look at the molecule. If it looks symmetric, it's not polar. It's asymmetric, it's polar. So the B is symmetric along the middle, but not along this axis. Okay. Volunteer, give me an atom. No, so for what work has to be no higher than neon. Boron. That's okay. I accept your apology. Let's give this a charge. -1. Okay. Okay. So B2 minus, and this is a lot of pressure here, person. I want to identify you, but some people have, and some people have not guessed the final exam question. So I wonder if you have. Well, I don't wonder because I know, but just want to toss that out there. Okay, B and B minus. There's only so many. B2, C2, N2, O2, F2, neon 2, with some random charge. Okay, this will come from a B and a B minus. One will have the minus charge, one will have the neutral charge. Let's write the electron configuration. At least this is how I do it. Other classes might do it a little bit different. 1s2, 2s2, 2p what? 2p1. Then 1s2, 2s2, 2p2. Okay? Now I'm not going to draw the core electrons, so I'm only going to draw the valence. I'll underline what I'm drawing. You don't need to write in the 1s. Okay, so we've got a 2s on this side and a 2p. And then on the other side, same thing, at the same energy level, 2p, 2s. Okay. Every bond, my class, or maybe other classes, I'm sure know this too, have how many parts? Two. The bonding and the anti-bonding. The anti-bonding is high energy, the bonding is low energy. The low energy is sigma or pi. Sigma subscript 2s, because it comes from the 2s. Sigma 2s star. The star or the asterisk means it's anti-bonding or high energy. Here we have 3 and 3, so that means there's going to be 3 bonding and 3 anti-bonding. Okay? What is the lowest energy level before I even draw it? The pi. Yeah, you have to know that if you are nitrogen or to the left of nitrogen, so boron would be to the left of nitrogen, a lower atomic number, the pi 2p is the lowest energy level. Then the sigma 2p comes next. Pi 2p star, sigma 2p star. Any boron, nitrogen, and boron, carbon, and nitrogen would follow this pattern. Put the little dots here to beautify it, make it look pretty. Shows where each molecular orbital came from. So, if you're feeling fuzzy, the middle of the diagram is the molecular orbitals. That's the orbitals of the molecule. The edges of the diagram under the B and B minus respectively would be the atom, or what we call the atomic orbitals. So a 2s or a 2p we used to call it just orbitals, but technically they're atomic orbitals. All right. Now all we do is fill in the number of electrons. So I've got 2s2. I'm getting this from where my finger is here. 2s2 is from the electron configuration. 2p1. For the other side, right there, 2s2. And then 2p2. 1, 2. So now I fill this in. I do it diagram by diagram. So I'm going to do the bottom first. 2 on each side, total of 4. 1, 2, 3, 4. Then I do the topmost diagram. 1 and 2, so total of 3. 1, 2, 3. Okay, so the third one pairs from the first one, or with the first one. What is the magnetism here? Paramagnetic. That means in the center on the molecular orbitals, there's at least one unpaired electron. That one electron's right there. So this has a magnetic moment or would respond to a magnetic field. Now I'm going to do bond order. If you're in another class, I think I would confuse you by explaining my way. So I'll just, I'm going to write some numbers here. Don't worry about that, just worry about the answer. Okay, my class, what's the first number? 3, 0, so it looks like it's 1 1/2. 3 halves. Okay, you'll get the same answer however you calculate that, if you know how to calculate it. Yes, I guess. It's a prerequisite. Yeah. Yeah. That's why Lewis is substandard. Yeah, right. That's a problem with Lewis. Yeah. And that's why. Any questions on this? This is going to be a pretty classic problem. Yes?
Do you fill the pie completely before moving on to the sigma?
Say it again?
Do you fill the pie completely before moving on to the sigma?
Yes, I'll do that for everybody, but the general alphabet principle is to go from lowest to highest. On each same energy level, you keep it unpaired, pair last, and then move up. I'll do an example for everybody. Is there somebody else down here somewhere? Okay. Let me mess up the diagram a little bit, so I hope you're done pointing and stuff. Yes? Yes. Okay, I'll answer that for everybody. First of all, electron filling. I'm going to mess up the diagram, so I hope you're done with it. If there was more than 3 electrons, the fourth one would go here. Then 5, 6. So you have to go up each time. Finish pairing, then go up again. 7, 8. I'm unpairing because they're the same energy level. Or they're singly by themselves. 9, 10, they're both paired now. Now I can go up again. 11, 12. Okay? So go in that order, do each level fully, move up, move up, move up. Okay. Why is the pi below the sigma? I'll just answer that quickly. It is something you need to know for nitrogen or to the left. It's the opposite. If you go the other way, one way to explain it is if you calculate or using spectroscopy find the energies, that just occurs. Some people explain that by the overlap of the pi orbitals. As the size changes as you go along, the horizontal row of the periodic table, and it happens to flip right there between nitrogen and oxygen. Yeah, that's mini explanation is that. I'll leave it at that for now. Okay. Did MO? Good. Valence bond theory, I don't have too much to say about it, but I guess I could say this. Let's say you have some p orbitals here, like this. So they're along the different axes of the x, y, z coordinate system. So different 2p orbitals. Like this. Again, McCurdy and some other folks should go plus and minus instead of the shading. Okay. If you are trying to form a structure from these, and you thought, well, if something's going to bond, it's going to overlap with the endpoints of these orbitals. Because these orbitals, so I'm talking about valence bond, because these orbitals are all at 90 degrees from each other, you would expect everything bonds always at 90 degrees. However, according to Vesper, that doesn't turn out in reality. Things have 109.5, or 120, or 180. Not everything is 90. So, valence bond, or just putting the orbitals together, doesn't get you all the angles, or bond angles, that Vesper tells you about. So, in lieu of that, we use hybridization. When we put hybrid orbitals together, that's where we come up with all these angles that happen to match Vesper, which we like, and to some degree reality. So Vesper and hybridization match, and it gets us those angles that that rarely are at 90 degrees. So that's about all I have for valence bond theory. Next, ionization energy. Let me see if I have that from my notes. I'll flip over. Oh, here it is, I think. Okay. I'm going to show you this. Yes, here we go. This is a table. It's also in your book. I just reprinted it myself. Okay. See those highlighted in brown numbers? So these are different elements. Their ionization energies, the first, the second ionization. So the first one removes 1 electron from the neutral, the second removes 2 electrons from the neutral, etc. Okay, look at the ones that are highlighted. Especially sulfur is an easy one to look at. So that 999.6. Do you see how it's smaller along the pattern? It's smaller than you would expect. So to lose that first electron from sulfur, it seems like it's much easier than you would expect, because if you follow the pattern, it's probably going to be a number between 1060 and 1256. But it's not. It's closer to 1000. Okay, why is that? Why is this energy for sulfur, and likewise these two, lower than what you would expect? Yeah, because if you draw neutral sulfur, sulfur is 1s2, oh my gosh, this is going to take a while, 2p6, 2s2, 2p6, 3s2, 3p4, did I get that? So, or I could have written, I don't know why I wasted ink just now, neon, okay, so neon, 3s, 3p, 3s2, 3p1, 2, 3, 4. Well, it's easiest to lose that fourth electron from sulfur. It's a low energy because once you remove it, you remove the pairing energy. So pairing takes a bit of energy to do. It's less energy when they're singly filled energy levels. So losing that fourth electron in a 3p4 or a 2p4 or a whatever 4 is going to be low energy relatively, because it's always lowest energy when either you have a half-filled shell, like 3p3, or a completely filled shell, 3p6. Either way of those would be more stable. So half-filled and fully filled are more stable conditions. Okay, so that's why you find these irregularities, which was a question in ionization energy. Or one reason you might find it. Yeah. What's the trend? You should know all the trends. It's a good reminder. Ionization energy increases when you go to the right and up the periodic table. So fluorine would be the highest. I'll ask everybody, is ionization energy a positive or negative number? Good, I asked, I guess. It's positive. You're putting energy in to remove electrons. Energy is going in the system. It's a positive number.